When you think of air defense, images of radar tracks, screaming interceptors, and sea-skimming missiles usually come to mind. Yet in recent years, a quieter revolution has been unfolding in Israel. Engineers and military planners have moved from explosives to photons, building a weapon that does not fire shrapnel or rockets but a focused beam of light. Called Iron Beam, this system marks a turning point in how states protect cities, bases, and infrastructure against rockets, mortars, and drones. It is a future-facing solution to an old problem: how to defend against fast, cheap threats in large numbers without bankrupting the defender. The emergence of Iron Beam is not merely technological showmanship. It is the product of doctrinal necessity, industrial skill, and years of incremental research into lasers, optics, and power management. Over the next half hour, we will trace why Israel needed such a system, how Iron Beam works, what it can and cannot do, and why its development matters not just to Israelis but to every country watching the next evolution of defensive warfare. Israel's security environment has long been defined by short-range threats. From the rockets launched by Hezbollah and Hamas to the mortar barrages that punctuate localized violence, the Israeli home front and military positions have faced waves of small, inexpensive projectiles that impose outsized political and economic costs. Conventional defense systems like Iron Dome have proven extraordinarily effective in intercepting many of these threats, saving lives and buying time for commanders and civilians alike. But effectiveness comes at a steep price. Each interceptor missile is an expensive piece of technology, and when dozens or hundreds of launches are required during a single escalation, the cost imbalance becomes striking. The growing use of drones, the potential for massive rocket barrages, and the reality of constrained budgets and supply chains combined to create a strategic imperative. Israel needed a lower cost, high-rate answer capable of dealing with swarms and tiny targets. Directed energy systems promised one answer: a way to convert electrical power into highly concentrated destructive energy without the recurring expense of missile interceptors. For a country that faces repeated short-duration offensives and asymmetric threats, a laser that can repeatedly engage cheap threats for the price of electricity presents a compelling economic and operational rationale. At its core, Iron Beam is an application of high-energy laser technology integrated into an air defense architecture. The system receives target data from radars and electro-optical sensors that detect incoming ordnance. Then a turreted laser tracks and directs energy onto a small area of the target until it fails structurally or its guidance is disrupted, producing and focusing tens or hundreds of kilowatts of power in a stable, controllable beam. Requires advances at multiple levels of engineering: high-power fiber and solid-state laser modules that can be combined coherently, precision beam steering optics that maintain focus across long ranges, thermal management systems that remove waste heat quickly, and control software that aligns tracking, pointing, and power delivery with split-second timing. None of these pieces is trivial. They require specialized manufacturing, battlefield-tough housings, and integration with detection and command systems that can hand off targets autonomously. Yet the appeal is obvious. Light travels at the speed of light, so there is effectively no flight time for the beam. The only delay is sensor detection and beam dwell time. That speed, combined with very low marginal cost per engagement, is what makes lasers transformative for the short-range defense problem. In practice, Iron Beam is not an isolated weapon, but a node in a layered defense network. Radars and early warning sensors first detect an incoming rocket or drone and classify its trajectory and threat level. A command system evaluates which interceptor is most appropriate given the target's speed, range, and value. For longer range or higher priority threats, missile interceptors may be launched. But for short-range rockets, mortar shells, and small UAVs, the laser is often the preferred option. Once assigned, the directed energy turret slews to the target, locks tracking, and focuses a narrow beam on a critical point, typically the motor, guidance surfaces, or thin structural components. The beam heats the material rapidly. Within seconds, the skin burns through. Motors fail, or control surfaces warp, and the projectile destabilizes and falls harmlessly. Because a single laser system can re-engage multiple targets in quick succession, it is particularly useful against salvos and drones where multiple interceptions are required almost simultaneously. That operational rhythm, detect, assign, focus, neutralize, is what allows Iron Beam to act as an economic complement to missile interceptors in a modern layered defense. Iron Beam does not replace Iron Dome, David's sling or arrow systems. It complements them. Each layer of Israel's air defense has a role based on range, altitude, speed, and threat type. Iron Dome handles short to medium rockets and is effective against many salvos. David's sling addresses medium to long-range cruise missiles and heavier rockets. Arrow is designed for high-end ballistic threats. Iron Beam takes its place alongside these systems as the economical short-range counter for large volumes of cheap threats and for small aerial targets like quadcopter swarms. Technically, integration requires common command and control protocols, interoperable data feeds, and rules of engagement that allow the system to select the most efficient effectors automatically. Operational exercises have shown that when the laser is networked into the larger defense grid, it reduces interceptor consumption, improves coverage for low-altitude threats, and decreases the risk of saturation during intense barrages. That integration is a model for how future air defense designs might combine kinetic and directed energy. Tools for cost-effective protection. Iron Beam moved from lab prototype to field testing through a series of controlled trials where it engaged representative threats under operationally realistic conditions. Engineers measured engagement times, accuracy, thermal loads, and system resilience, while operators developed tactics for handoff between missiles and lasers. While some testing occurs behind closed doors for obvious security reasons, the results Israel has shared publicly indicate a mature capability in specific engagement envelopes. Combat readiness is not only measured in technical specs but also in doctrine, training, and logistics. Having crews who can maintain beamlines, supply chains for power and optics, and protocols for operating alongside conventional interceptors. The transition from controlled tests to operational deployment requires an iterative process of feedback from exercises and limited operational use, a process Israel has undertaken deliberately to ensure the system performs reliably when called upon in conflict. Looking forward, the natural path for directed energy systems is scaling. Higher power to engage more distant or hardened threats, better beam control to resist atmospheric distortion, and mobile power solutions that allow deployment across theaters. Advances in solid-state lasers, fiber amplification, and power electronics will push capabilities further, while cost reductions could make lasers attractive for other nations facing swarm threats. Israel's position as an early deployer creates export and partnership opportunities, where allied nations could field adapted variants for base protection, shipboard defense, or critical national infrastructure. Yet exportability is constrained by dual-use concerns. The same technologies that enable defense can also enable offensive capabilities if misapplied. So export controls and partner vetting will shape how widely the technology spreads. Strategically, the next decade will likely see incremental improvements rather than sudden leaps. Higher output, improved robustness in poor weather, and tighter integration with sensors and effectors, transforming lasers from specialized niche systems into mainstream defensive tools. If you found this deep dive into Iron Beam useful, subscribe for more documentary-style analyses of the technologies reshaping global security. Tell us in the comments which angle you want next: a technical teardown of laser components, a scenario analysis of Iron Beam operating alongside Iron Dome in full conflict, or a global survey of directed energy programs. Like, share, and hit the bell so you don't miss the next episode. The future of defense is being written today, in labs, test ranges, and the quiet hum of power supplies that turn photons into protection.